Hi, my name is Scott Crowder, and I'd like to talk to you today about quantum computing. The reason why we're so interested in quantum computing is because we may think that classical computers can solve any problem if they just get big enough, but unfortunately that's not true. And unfortunately, we still have a lot of problems that would be great if we could compute them that would make massive impacts to our society. So just to give you a couple examples. Today we use, some people estimate up to 2% of the total energy that we consume on just making fertilizer. We know that in nature, bacteria are much more efficient in doing this than we can do it as humans. So being able to understand that chemical reaction better could have huge implications for our society. We'd love to be able to more efficiently create energy and really address our climate change problems. And again, understanding chemistry better will allow us to make energy production much more efficient. And as an example recently in the Suez Canal proved, we live in a very, very highly complex interdependent world where being able to predict and model the implications of events on our financial systems are really important. They would improve the stability of our societies and help us drive growth. And finally, this world that we've lived in for the last year and a half has shown us how important it is to make very rapid improvements in our drugs. So drug discovery is of critical importance to our society, and be able to, instead of leveraging wet benches all the time, be able to compute the implications much more efficiently would have huge benefits to our society. So the good news is we're really at the beginning of a completely new age of computation. And we've been doing classical computation for a very, very long time, well before the 1940s. You could argue since we were counting dinosaurs in caves, we were doing classical computation with our fingers. And in the 40s, we invented universal electronic digital programmable computing devices. And this transformed the world. It launched the IT revolution and has had implications across society. Quantum computing is a completely different type of information science. It's brand new and is based on quantum information science, quantum mechanics. Now, the major problem with classical computation, even though it has solved a lot of problems and made our lives significantly better, is that it scales linearly. If you want to double the power of a classical computer, you need to basically double the bits or more. Double the amount of memory, double the amount of storage, double the amount of bits in your processor to basically double the power of your processor. Quantum information science leverages quantum mechanics and it scales fundamentally differently. And that's why people are so excited about it. It leverages superposition to allow you to look at an exponentially larger set of state than you can using classical computation. Another major difference between the late 40s and today is that in the late 40s, if you wanted to interact with the first electronic digital programmable computing device, you needed to be in the room plugging and unplugging wires. Since then, we've invented this little thing called the internet. So if you want to interact with a real quantum computer, you can just leverage the internet. And this has allowed us to make quantum computing much more accessible than digital computers were in the early days of digital computing. The second thing that's changed over the last 70 years or 65 or whatever is that as humans, we've created this entire software stack for classical computing. And we can leverage that for quantum information science and quantum computing. We don't need to create new languages. And that has also made it a lot easier for people to get started playing around with quantum computers. So if you can program in Python, you can program a quantum computer. And we really hope that making it much more accessible, both from a programming point of view, as well as from a pure access point of view, will enable us to make much more rapid progress with quantum computing than we did even with digital computing. Okay, so again, why do we care? We care because, unlike in popular science, when you think, well, computers just get bigger and bigger and bigger, they'll be able to solve everything. Classical computers fundamentally are not good at scaling for certain types of problems. There are computationally hard problems for classical computers. Those things are usually the ones that, as you add a new variable, the amount of computation you need goes up by a factor of 2. So it scales on you really poorly. It blows up on you. So quantum computers are the only novel hardware where really changes this. It's not about doing like a GPU more things in parallel that just leverages classical computing again. It's fundamentally a different paradigm because it uses quantum mechanics. Now, we know that quantum computers are not going to be good at solving every single problem that's hard for classical computers. We've proven that theoretically that is not the case. But we have proven theoretically that there are a set of problems that are really difficult to compute with classical computers that are easier and much more efficient with sufficiently large and sufficiently high quality quantum computers when we get there. One example of that is factoring. So factoring, A times B equals C. Very, very trivial for a classical computer. If you give it two large numbers, A and B, to multiply them together and spit out the answer C. That's easy for a classical computer to do. Going the other way, fundamentally, classical computers suck at it. So if you give a very large number C and say, what are the two largest numbers, A and B, that multiply together to get C, classical computers have a really difficult time at doing that because it needs to look through tons and tons of permutations. And that problem of looking through the permutations is one of those problems that scales very poorly. So because of that, because A times B is equal, multiplying those together is easy and going the other way is hard, we've leveraged this for a lot of our cryptology. A lot of the world's cryptology is based on that simple fact that factoring is really, really hard for classical computers. But there are other, potentially, more societally beneficial types of problems, types of math that it has been proven theoretically that classical computers will be much more efficient than classical. So example of that, well, one of them is quantum material simulations. So simulating the real world of quantum mechanics. So since quantum information science leverages quantum mechanics, it kind of makes sense that it has a good sweet spot in trying to solve those problems. Those problems are the same reason why quantum computers scale exponentially, not linearly. That's why those problems scale exponential, because in an atom or a molecule, every time I add a new spin orbital or electron to the system, I'm doubling the terms in the equation that you need to solve in order to solve the overall, we basically to solve the chemistry of that entity. And because of that, it doesn't sound like, oh, doubling, that's not a big deal. Yeah, it's not a big deal if you go from 2 electrons to 3 electrons, you're going from 4 to 8. But doubling really catches up on you quickly. So when you get to 50 spin orbitals, that's 2 to the 50th, that is a larger amount of state space, number of terms in the equation, than there are in the world's largest supercomputers. When you get to about 150, 2 to the 150, that's about as many atoms are in the planet Earth. And you get into the 300s, you're talking about more atoms than are in the known universe. So it's a safe bet to say that classical computers will never, ever, ever, ever get large enough for you basically to be able to hold that much state space. But you can do it with quantum information science. You can do it with quantum computers. Again, when they get low enough error rate and they get large enough. But large enough is on the equivalent of hundreds or thousands of qubits, logical qubits, not the number of atoms in the known universe. That's why people are so excited about it. Also, it sounds really cool because it's sci-fi-like. So what fundamental principle of quantum mechanics does quantum computing leverage? It leverages superposition. Overly simplistically, in a classical computer, if you're in a binary system, your bit is either in the 0 state or the 1 state. In quantum computing, your quantum bit, your qubit, while you're doing the computation, not after you measure it, it either collapses to a 0 or a 1, but while you're doing the computation, it's in a linear superposition of the 0 state and the 1 state. You can think of it very simply as alpha times the 0 state plus beta times the 1 state. And the probability overall is 1. It's going to be in one of those states when you measure it. But while you're doing the computation, it's in that superposition of states. And that's what's so different, and it's subtle, but that's what gives it the ability to do things in a very radically different way than you can classically, with no comparison. The second thing that allows your algorithms to be more efficient is that a special kind of superposition called entanglement, where you basically have two qubits and you can entangle the states. So the state of one qubit depends on the state of the other qubit while you're doing computation. And there's no classical equivalent to that at all. In fact, this is the thing that freaked out Einstein. He really didn't believe it, the spooky action at a distance. But it's fundamentally how our universe works, how quantum mechanics works. And we're leveraging those principles to do a very, very different kind of information science that for certain types of math is proven to be a lot more efficient than you can ever do classically. So what are the elements to the actual computer? So at its heart, you need something that holds a quantum state, a qubit, that's easily programmable, and you can measure it. You can read it out. So for us, for IBM and many others, we use something called a superconducting transmon qubit, that thing that holds the quantum state. That's a pretty simple element. It's basically a nonlinear inductor and a capacitor in parallel. So it basically, resonates at a certain frequency. The reason why you need it to be nonlinear is so your energy gap between the 0 state and the 1 state is a different energy gap than 1 to 2, 2 to 3, et cetera, et cetera, et cetera. The other thing that you need is to be able to interact with that qubit. Because if it just exists out there and you can't interact with it, then it doesn't really have much value. So basically those squiggly lines in the picture on the left is basically resonators that basically allow you to have qubits interact with each other. And there's a set of resonators that go out to be able to measure the state of the qubit. And that's a probabilistic measurement. Again, based on the superposition of it, it's either going to default or collapse to a 0 state or a 1 state, with the probability defined by the square of alpha or the square of beta, the two terms in that equation. All right, so we've got this qubit. How do you program it? You're programming it by basically sending microwave pulses down to it. That basically makes it rotate around the Bloch sphere. So you can basically change the amplitude and the phase of the alpha term and the beta term in your linear superposition. And if you want to basically get two qubits to entangle with each other, you basically send a microwave pulse to one qubit that has the frequency of the other qubit, and that basically creates an entangled operation. Usually you think of it as a C-NOT or a NOT gate, a controlled NOT gate. So based on the state of qubit 1, I can either rotate or not rotate qubit 2's phase. Or basically overly simplistic, if you just have it as one-dimensional, how far from 0 to 1 you go. Now, this is not science fiction. These things are real. For example, right now, we've got 23 quantum systems available on the cloud. This is just a screen capture I took last Friday of all the systems available from IBM Quantum. They range from 1 qubit to just do some really simple experiments on qubit control, up to 65 qubits, which is kind of state of the art today for the largest systems that are out there. So you can see basically here all the statuses, and as well as having like simulators that people can do simulation on, available on the cloud. An example of what one of these things looks like. I mean, the picture on the left looks like just a standard everyday processor when it's all packaged up. But within there, you've got 65 qubits today, that's state of the art. And the picture to the right is basically the connectivity map between the qubits on that processor. Now, as you can see, basically on the processor or the logic unit, it is very different than today's VLSI processors. The only elements that are on there are really the qubits and the connections between them. There's no predefined circuit There's no predefined instructions in silicon. What's in silicon is really just the qubits themselves. So to create the circuits, it's really software defined, which is kind of cool when you think about it. And these circuits are basically the computational building blocks for that quantum logic unit. They basically consist of basically all the qubits in the system. You initialize it to a state, usually the ground state, and then you apply instructions to it. Hadamard gates, CNOTs, and typical Boolean type operations. And then at the end of the day, you measure. And when you measure, you collapse back to zeros and ones that come out. So how does this work in practice? So in practice, basically, you're sending signals, through your room temperature electronics down to that cryostat that keeps your qubits at near zero temperature. And as I mentioned before, the instructions are sent into, basically translated into microwave pulses that go down to those little qubits. Basically, you get a measurement signal, and then basically you measure, microwave signals that are then translated into classical zeros and ones and sent back. So I mentioned cold. It's really, really friggin' cold. You need to keep the processor, no, sorry, it's not the processor, the quantum logic unit that has the qubits as close to near zero as you can get. Can't be 0, 0, because if it's 0, 0, nothing's going to happen, but really, really close to that. So for us, it's around 15 to 20 millikelvin, which basically, if you think of things in a log chart, is the same distance away from the temperature out of space as the temperature out of space is away from, basically room temperature. So it's really, really, really cold. All right, so what is it going to take to make these quantum computers real? It's going to take three things. One, we need to get the error rates down. We need to improve the quality. Two, we need to get the throughput up. We need to improve the capacity. And what technology underlying you choose to basically will tell you how quickly you could possibly get that to happen. And that's why we've chosen superconducting qubits, because it's on the order of nanoseconds per instruction. And then variety. You need to basically be able to create more complex circuits, dynamic circuits that take into account basically feed forward to allow you to do error correction and things like that. So real quantum programs are more complex than what I just said. Real quantum programs are a hybrid of classical and quantum computation. There's no memory in that qubit chip. There's no storage there. There's no classical computation there. So to do a real quantum algorithm, it's a combination of classical instructions and quantum instructions. And that entire program needs to be run efficiently. So what I mentioned before was really a simplification. And in reality, your quantum computer is that hybrid mix of classical resources and quantum resources. So your program actually goes and lives on a hybrid compute, cloud compute environment, gets run in a container, and just those circuits are run on your, what you think of as a quantum computer, but really is just a logic unit. All this, if we're going to be successful, really needs to be frictionless from a developer point of view. They need to be able to use the same tools, the same languages, the same code, etc. And just as a simple example, just an example of just taking the APIs and throwing it into an Excel spreadsheet so you can call a quantum computer from Excel. Once you've created that frictionless environment that allows you to call basically a quantum model, you shouldn't have to change your workflow. It's just instead of calling, like in Cplex, a optimization module that's classical, you basically call a quantum module instead. That's what we mean by frictionless development. So we put together a roadmap and published it, and you can, if you're interested, you can learn more and go look at it. But both for the hardware, that gets us to over 1,000 qubits by 2023, as well as the software and the larger hybrid system that allows you to basically create these libraries of quantum algorithms to solve the problems that we talked about at the beginning of this beginning of this talk. And finally, you need to be able to build a community. And to build a community, it's really about providing access and making it open. Again, as I said before at the beginning, This is brand new technology. We fundamentally believe that success is going to require as many people as can get access to this technology, getting access as early as possible. And we're really excited about the fact this is a brand new technology. We have the ability to shape the future workforce and make it a diverse and inclusive workforce. So we put a lot of focus on education, inclusivity, and there's a lot of great material out there. Qiskit, YouTube, the textbook. I encourage you to go look for more. I apologize for this fire hose on what is quantum computing. I hope you enjoyed it, and thank you very much.